Hey guys, welcome back to Unit 8 of the ICP Final Study Guide. Let's take a look at nuclear radiation. There's some fun stuff here. So question 1 says complete the table, right? We're given alpha, beta, and gamma radiation, and we're supposed to fill out this chart, right? So what is the symbol for alpha radiation? Well, the symbol for this one is going to be that, 4 over 2 alpha. And remember, when we write this in isotope notation, this top number is our mass number and bottom number is our atomic number. Composition is we're going to have 2 protons and 2 neutrons. This will change the mass number by 4 and change the atomic number by 2. And this is very easily stopped by paper. Next, take a look at beta radiation. Beta radiation symbol is 0, -1, and then this weird B thing, right? Let me try to draw it better. Yeah, that's the beta. So when we have this, we're gonna have we're composed of 0. How do I make this? It's just gonna be an electron, right? Just 1 electron is how you'd call it. It would change the mass number by 0 and change the atomic number by -1. And of course this is stopped by aluminum. And as you probably noticed, as you go down from alpha to gamma, the strength increases. So the more you go down, the stronger it is. Last but not least, gamma, we have 0, 0, Y. Okay, that's a horrible Y. See if I can, there you go, 0, 0, 0, 0, Y. You're supposed to write it in those fancy Greek letters, but I don't really care. The composition is just going to be a kind of like a photon, like a light photon, we'll call it. Right? There's no protons, there's no neutrons. It's going to have 0 for mass number change and 0 for atomic number change. And of course, this is the hardest type of radiation to stop and can only be stopped by lead. So if you go to the dentist to get your teeth x-rayed, or the hospital because you broke a bone, they're going to put that vest on you that's super heavy. That is the lead vest that's protecting you from the x-ray radiation. So kind of something similar to that, the gamma radiation, and it can only be stopped by lead. Moving on to question 2. The following atoms all undergo alpha particle emission. Write the complete nuclear equation. So what did we say the alpha, scroll up a little, what did we say the alpha particle was? Well, we're going to have 4, 2, alpha, right? And remember our law saying conservation of mass, the law of conservation of mass. So whatever we have for here must match this plus this and this plus this, right? Of course, these are numbers we don't know yet. So all we have to do for this is, since the arrow is there, we can subtract 4 from 210 and get the mass number. So 210 minus 4 is 206, and then 84 minus 2 is 82, right? And so we just need the symbol that goes there, right? And how do we figure that out? Well, 82 is our atomic number, which is the amount of protons, which is correspondent to the number with the number of the element it is. So what is the 82nd element? It is going to be lead, Pb. So then this symbol here, we're going to put as Pb. That is our balanced nuclear equation. Moving on to question 2. This is also alpha decay if you were not paying attention. Let's zoom in a little bit more. Perfect. We have something here. Okay, this is supposed to be an arrow there. Let's draw that in black. I don't know. It keeps cutting this off. Alright. We have 238, right? So we have 4 over 2 alpha. So 238 minus 4 is 234. 92 minus 2 is 90. So going back to our periodic table, let me move back and forth a little bit here. 90 is going to be the element thorium down here. TH, thorium. Let's see here. Zoom in a little bit more. And so this element is going to be TH. And that's your balanced nuclear equation. It's not that bad. So question 3 says these atoms all undergo beta decay. And if we remember what beta decay is, it's going to be 0, negative 1, and then that fancy B thing, right? So of course the arrow is in the same spot for both. So the way to solve it is going to be the same for both. So 0, negative 1, beta. So in this case, 6 minus 1 will give you 6 plus 1, right? Because this number has to be 1 greater in order to get 6. So 14 and 0 have no change whatsoever. So you're going to have the same mass number, but this time you're going to have 6 plus 1, which is 7. So if you all do not know what the 7th element is, 7th element there is nitrogen. Okay, so that right there is going to be nitrogen. Moving on to the next question, in a similar fashion, we're going to have beta decay right there. And 90 plus 0 is 90. And 38 minus 1 is the same thing as 38 plus 1, which gives you 39. And the 39th element on the periodic table is yttrium. Y. Alright, so that will be Y. Okay, let's write that differently so it does not get confusing. Yes, Y. Alright, moving on to question 4. In the space provided, define each term, give examples, and create a diagram. Alright, so we have fission versus fusion, right? So the easiest way to remember these that I found was that fission and fusion, well, let's actually draw this first and then we'll talk about it. So fission is where you have, this is the stuff we can accomplish right now safely. So this will be kind of just like you have, I don't know how to draw this, but we have one like particle that's going to separate into 2 individual particles, right? It fizzes out, so that's in fission. While fusion, we're going to have 2 individual particles that merge together to form something new. And so the definition of each is fission is where an atom splits to produce insanely large amounts of energy. Alright, and fusion is where an atom fuses together to produce large amount of energy. Large amount of NRG, and that's just short for energy. And so the easiest way to remember this, where it occurs, right? Fission we can accomplish, but fusion occurs in the sun because there's a U in it. Sun. It's just a kind of a dumb mnemonic that I use to memorize these. And so an example of these interesting. An example would be, I don't know that you need to know specific chemical fission examples, but well, you could technically do uranium 235 plus a neutron equals energy. And in this case, energy is literally energy. And for fusion, you could do let's see. Oops, that's the wrong button. That was not good. Give me 1 second here. Go back. All right. Deuterium, an isotope of a hydrogen, plus tritium gives you energy. And I don't know that you need to know these examples. Even I had to Google them. I don't know. I can't even think of these examples off the top of my head. So yeah, I don't think you need to know them that deep. Just know what they are. They split to produce, or fuses to produce energy. Just know that, and you know, you'll be fine. You don't need to know like specific examples. Just know that if it occurs in the sun, this reaction will occur in the sun. That is fusion. We are not capable of producing energy efficient and money efficient fusion yet, but we're getting there. All right, question 5 says, what do fission and fusion reactions have in common? Well, the major thing that they have in common is they both produce insanely large amounts of energy. And that's a major commonality of fission and fusion. Last but not least, we have a classic half-life question. I love half-life. It's very easy. You do not need to use any brain power for these questions. The half-life of an isotope is 2 years. We originally had 100 grams to start with. 100 grams start. How many grams decay after 6 years, right? X grams after 6 years. Alright. Oops. Okay, so we have 6 years worth of decay, and each half-life is 2. So 6 years divided by 2-year half-life is going to be 3 half-lives, right? 3 half-lives. So we're going to undergo 3 half-lives for 100 grams worth of solid, or radioisotope. So in order to do this, we take 100 grams and divide it by 2 3 times. That's what half-life means. You have half of what you started with, except we're doing that 3 times because we have 3 half-lives. 100 divided by 2 is 50. Divided by 2, that's our second half-life, 25. Divide that by 2, that's our third half-life. We're going to have 12.5 grams of radioisotope. That is our final answer. 1 half-life. That is our second half-life. Okay, I wrote this wrong. Give me a second. There's supposed to be a 2 there. This is 12.5 grams. There you go. So that is our first half-life. That is our second half-life. And that is our third half-life. And so the answer is 12.5 grams you will have after 6 years. It actually asked for how many grams decayed. Okay, that's not hard to calculate. Give me a second. So we have 12.5 grams that decayed, and we originally had 100 grams. So all you have to do is subtract it from 12.5, which will give you, mental math, 87.5. 87.5 grams decayed. Usually it doesn't ask for that, but I guess I should have read it better. Life lesson here, folks, is to read the question properly, because it might do this, kind of, I don't know, weird way of asking you. to subtract. So the amount of decaying happen is going to be 87.5 grams, but you'll end up with 12.5 grams afterwards. That brings us to the end of Unit 8 for nuclear stuff, nuclear chemistry. And we'll see you back in our last unit for solutions, acids, and bases. Thank you.